motivation, we still use elliptic error multiplication in precompiles, especially EC recovery and pairing, and we use in recursion. And it's worth to say that mostly we use multi-exponential for not like simple multiplication, multi-exponential. So let's start. It's a classical algorithm of elliptic error scalar multiplication, what you can see in Wikipedia. And we have 3 problems here. First problem is that every step in circuit, we need to compute 2 points and use select between them. And select is quite expensive. Second problem, exceptions we can actually have exception when we adding point. And third one, loop start with point and infinity. This is 3 problems. How we solve this? We actually use representation. It looks like binary representation, but we use 1 and -1. And it's the same algorithm, but with representation. And what actually change that now we have selection between 1 point, like Q and negative Q. And in the practice, when you choose between 2 points, you need to make select between X and then between Y. Now we just need to make selection between bytes, so it's like easier. Second one, we start our accumulation from P. So we have an infinity point. And third one is like a bonus, because in every step, we have point 2p plus minus q. And we actually can use this trick. This trick will reduce to multiplication. So, but we still can have exception. And our exception can be in addition, and the potential point can be infinity. And we have 3 solutions. First solution in the check and affine select. It just we wrap point, affine point with flag. Flag will identify that it's point infinity or not. Second one, we use exception-free projective point, but this trick this solution works just with prime order Q. And third one, we use offset generator, and actually this works for both Q, prime order and not prime order. And let's look at our algorithm with offset generator. So we add our offset generator in the beginning. Here we make accumulator to a generator, add the counter. I will explain later why. And in the end, we divide. So why we actually add counter? Every time when you have a generator, you make a double time point, and this generator become bigger, and you need just subtract in the end to get the original result. That's why you multiply this generator to amounts of doubling. And it's good to say that as a generator, what we get shouldn't be an order of 2. Yeah, and let's look how these 3 methods work from different curves, prime order and not prime order. And check and affine actually work for both easily. Projective point, it exists just exception-free formula, just exists from prime order curve, and actually it's easy to multiply this point and infinity, wrap this point in that. And last one, offset generator, we take a generator over extension field. So we get point in extension field, and we add every other point to this extension field, and we will get, of course, point in an extension. So we never will have exception. And in the case when we have not exception free, we just use a random generator in base field. For balance, it's easier. We don't need to take offset generator over extension. We just take generator infinite point over base field in cofactor. Next, also, previous algorithm will perfect compute with simultaneous multiple point multiplication, and And main in this multiplication is precompute. We count all possible combinations, send them into local memory in a form point address, and also we use all this algorithm with automorphism. But I wouldn't tell about automorphism, it's little later. So in main multiplication, we break our scalar into windows, 2 chunks, inherent chunks, read the combination from memory, and add this point we get from memory to accumulator. And during the read, we make a queue to memory for future proofs. So this is example. This is example now. We have a lot of points, and we have a lot of scalars, and we have window 4. What do we actually do in precompute? We create a lot of combination with different scalars, possible scalar. And in the main multiplication, we break our scalar to window 4 and just take point to this address. So, proof of correctness. Don't forget that we actually work in ZK. So we need proof our memory. And during precomputation step, we make a request, write request, and during main step, we make read request. So correctness of permutation. We take all to this queue, split to each other, and sorting them. And we prove that we have exactly 2 power of window minus 1 points. So we make sure that we haven't any another points for make not correct proof. And of course we need to prove sorting. And for sorting we have correctness of sorted, and we have different approach for this. This is 3 approach what we have. First one is selection tree. We use select. Our selection flag will be our address, and we just take point what we need. Run with Luxemon is actually prove with networks. And last one, we prove that sorting is right is using precomputation. And you see, it's element and unsorted queue, it's element sorted queue. So we make a product, but those x is a hash. So every time, for every element, we add this hash. And if this equation will equal, that means that sorting is right. So it's not another use. And it is whole blocks what we have, actually. And you see that we also have another generator, adjective generator, because in precomputation, we make a combination and potentially can be 0, 2, because we don't use any generator. So we wrap this with a projective point, wrap with flag, and add for adjective generator, who is also an extension. And in finalization, what we made, we just subtract every other generator what we have. I explain how we subtract offset generator. With this adjective generator is much easier because we have this generator of order of 3. So we just 3 select, like accumulator plus this adjective generator, and accumulator minus this adjective generator. So I have a time, so next topic. Oh, not topic, results, of course. And you see the most optimal strategy is selection tree. It's selection tree, believe me. And with window 4, and we tested this on 4 points and 4 scalar. It's multi-exponential. And actually, good to say that multi-exponential with hash set also will be optimal. Just depends from which hash do you use. You can use fast hash, and you will get less constraints. Constraints are our metrics. And it's good to say that we tested this to be a curve. Next topic, it's a pairing. So this is picture of extension, and our motivation to get element in extension, power of 12. And one trick what we use is torus-based compression. We got, after final exponential, we got point in right groups, and we can, of course, compress points, and you intake elements in a field of tension of 6, or in the compress, decompress, making point back. So next, for what actually we need this? For reduce structure formulas. What we use for final exponential, it is multiplication, squaring, inverse, and Frobenius. If you look at formulas, after we have a final exponential, and a final exponential consists from easy part and hard part. And we use this torrent compression actually for hard part, but we can actually have exception. We can show points 1 and -1 in a torus. It's exception. So to be sure that our hard part chain haven't any exception, we need to check these 3 equations. And another trick, what we use subgroup check. It's in native, it's cheap too, because we have constant scalar and we can use pre-compute or without, we have a constant scalar and we don't need that it's safe at the offset generator or something. But what if we use this subgroup check during Miller loop? So during Miller loop, we get scalar, what we need for our formula, and we use Frobenius endomorphism. So we just reuse what we compute in Miller loop. Then our subgroup will be cheaper. So the next one is subgroup check for BLS. It's different formulas, but the same. We have Frobenius endomorphism, and we can get Frobenius endomorphism in Miller loop. And also I wanted to add, for previous slides, that we don't need to check that point is in G1, because when we switch curve to a twist, we actually do this. We actually check this point. So that's all. Thank you for your attention.
Yeah, it's super exciting to see how to hack the mathematical elliptic cryptography. We have 2 minutes for the Q&A, so yep.
So you said that it's too expensive on BLS 12381 to do the projective coordinate exception-free multiplication. But if you use subgroup checks, you don't need to, you're sure that you're in the correct subgroup, so there's no problem.
Yeah. You ask about subgroup check? Because
I'm asking about the scalar multiplication. You said that we cannot use it if we have a large cofactor, but if we use subgroup check, we are in the proper subgroup, so there is no worries about
you just want to use subgroup check every step?
But you can use at the beginning, and then you're sure that you're in the correct subgroup.
Okay, then question for you. What we will do doing in multiplication? You can actually get infinity point in every moment.
You cannot get infinity point if you use the projective coordinates exception-free.
For BLS?
Yeah.
Yeah, for BLS, I don't think so. It's exception-free formulas.
The paper from Rennes 2015 is exception-free for everything.
For BLS?
Yeah.
Interesting. I would like to read. But I know exactly that I'm pretty sure that it exists from Ben, because I checked. But when I implement this, I try to find the exception-free formula for BLS, and I didn't find. So I decided that so it's not
we can discuss afterwards.
Yes, but actually offset generator is not, it will be even cheaper, I think, add to generators and use projective point.
Yeah, hacking the algorithm is so nice. I mean, so fun. But actually, we don't have time, so we need to go to the next topic. So please go to some backstage, and please come to Olena to talk about the further discussions. Yeah, thank you so much.
Thank you.